Okay, we know that magnetic fields are created from moving charged particles. Mu naught over 4 pi QV cross R hat over R squared. Okay, and it's interesting that magnetic fields depend on how perpendicular the velocity is to the point you're measuring it. Okay, so that's what this cross product does. So B fields have two things that are unique. One, they depend on moving charges, okay, and they're about perpendicularity. Well, we've all seen magnets stick to fridges, and they have a very perceivable, measurable force. So what about magnetic forces? Well, you can do a number of experiments of watching charged particles move in the presence of a magnetic field, let's say from a fridge magnet, and we can empirically determine the force on a charged particle. So this is empirically done, just like you do with Coulomb's law. That was empirically determined by taking a lot of measurements. Same thing here. This magnetic force is equal to this, or is proportional to the size of the charge, how big the charge is, how fast it's moving, and then how perpendicular it is to a magnetic field from something else. Okay, so the force, so this is creating a field from some moving charge. So a moving charge can create a field, but in order for a charge to feel a magnetic force, it has to be moving. So it's important to distinguish that this would be from some sources, and this together is a test charge. Okay, so something's creating a magnetic field at a location in space. It could be another charge, it could be a wire, it could be all sorts of different things. It could be a loop, a dipole, but this is being created at some location in space by something else. And generally we're not worried about that something else. We just say there is a B field there. But then we say, well, what happens when I put a charge in that space and it's moving? Then we can measure that force. So this is how we find the B field from a source. This is how we find the force on a test charge because of that source. Okay, so that's important to keep these straight. But what's interesting is that the force has those same two unique conditions. One, the charge has to be moving to feel a force. And two, the force is only significant if it is moving perpendicular to a magnetic field. Okay, so to make sense of this, first of all, let's remember what cross products mean and just talk about sizes of forces. So the size of the force is just going to be QVB sine of the angle between them. Okay, or like I like to say, it's QVB perp. Okay, so it only depends on the piece of the magnetic field perpendicular to velocity, or we could say V perp B. Okay. So we can, if the B field's easy and it'd be easier to break up the velocity into components parallel to and perpendicular to the B field, then this might be an easier way to calculate it. Okay, but all of them are really just emphasizing that I care how perpendicular they are. So that's how big it is. The direction is given by the right-hand rule. So all of these have a right-hand rule direction. Okay, so again, I'm using this RHR to stand for right-hand rule, and the hat means direction. This is how big, that's the direction. So the direction is probably best with a few examples. Okay, let's say we have a charge here. We'll assume it's a positive charge, and it's moving to the right with speed v, and it's in a region of space where the magnetic field is pointing up. Okay, now be careful. This B field is not from this charge. Now, because this charge is moving, it's creating a B field, but that's not the B field we're talking about. This B field is from something else, some sources somewhere else. Okay? So it's easy to confuse these two. Now, this might be creating a B field that could act on something else over here, but we're not worrying about what B field this is creating. This is created by something else. Okay, so we have this B field that's pointing upward. Okay, and we'll just assume that it's at this location in time. It's pointing upward. Okay, so if that's true, then the force on this test charge, here's QT, okay, it's our test charge. The force on this test charge is given by the right-hand rule, where V is the first thing in the cross product, B is the second thing. Okay, so here comes my right hand. V is pointing that way, so here's my first finger. B is pointing up, which forces my thumb to point out at you. So if this was a real situation, that charged particle would curve up out at you because that's the direction of the force. Okay, so the force is given by that symbol. That means out. Okay, or I can just say out. Okay. Force is out. Let's do another example. Let's see. Let's suppose the same test charge traveling in the same direction, but now I have a magnetic field everywhere here that's into the page. Okay, so my magnetic field is into the page, or I can show it by the symbol of a cross. Okay, that X. Okay, so right-hand rule, it's V cross B. So this is the first thing, this is the second thing. So V is still this way, but now B is into the page. So I point that finger down. That forces my thumb to point, keeping it perpendicular to the first two. Sorry, let me do this a little better. Pointing up the page. Okay. So V is that way, B field's down away from you, forcing my thumb to be up the page. So the force, I'll draw it like this. The force acting on this charged particle, because it's moving, is upward. Okay. All right, so that's an example, two examples of using the right-hand rule to figure out the direction. Okay. Now what if we had something kind of like this? Here's our charge, and the magnetic field in this region of space is like that. Here's V, here's our test charge. What would be the direction of the force then? Okay. Well, what I care about is how perpendicular they are. And so I just need to draw this in terms of its components. And this would be B perp. This would be B parallel. This part of this magnetic field is parallel to V and does nothing. It doesn't affect this charge at all. This piece does cause a force on it in the same way this one. It's just not as big because it's only a part of the B field instead of the whole B field. So I get that B perp is now smaller because theta is not 90 degrees. They're not perpendicular, so B perp is a little bit smaller than B. Okay, so that's a great example of doing this. Now there's one small little catch that even sometimes catches me if I'm not really paying attention to the nitty-gritty, is Q can be negative. So I assumed all these charges were positive, and I did state that. But if this happened to be a negative charge, well, then your end result is just opposite whatever you got with the right-hand rule. You're just throwing a minus sign. Okay, so in this case, if this was a negative charge, F would be in. And in this case, if Q is a negative charge, then F would be down. Okay.